Let us see a simple example of how to describe in Verilog a 2:1 multiplexer but using Dataflow modeling. So let's open model cell. Let me create a new project. I'll call it as mux221. I'll create a new file, Verilog. Also give it the same name, mux221. I'll say OK. So let's define the module and the ports first. So as you know, a 2:1 mux has one output Y, two data inputs and one select input. So therefore let's define or declare the signals output Y. Data is of 2 bits because a 2:1 mux has 2 data lines. So I'll say input 1:0 data and input select. Because a 2:1 mux has a 1-bit select input or a single select input. Now we are going to use Dataflow modeling, which means we are not going to be using always. What this means is that we have to use assign statements. So we will assign something to Y. So Y equals something. Now this something has to be explained by means of an equation or description because we are not using structural modeling here. So over here, I will write a way through which I say that if the select input is 0, then data of 0 must be the output. Else, if the select is 1, then the data of 1 must go to the output Y. However, we are not allowed to use if, else and such statements outside always blocks. So therefore, in this assign statement, there is a provision for you to define it something like this. So I'll first write the signal name whose condition I'm checking, that is select. And after that, I'm going to put a question mark. Then, after question mark, there are going to be 2 sets of brackets separated with a colon. And in the first bracket, if select is equal to 1, then whatever is inside the bracket, that will go to Y. And if select is not equal to 1, whatever is in the second bracket, that will go to Y. So if select is 1, then data of 1 must go to Y. And otherwise, it should be data of 0. That's it. And then I will say end module. Let us see whether it works. And you can see the compilation was successful. So let us quickly simulate it. So I'll add this. So data, I can assign it as some clocks of some frequency. Let us say I'll assign it as 200 and 400, or let me make it 500. And the select input, I'm going to give it a clock of 100 and let me run. So as you can see over here, first select is 1. So therefore whatever is data of 1, that will be the output, which is also 1. Here select is 0. So whatever is data of 0, that will be 1. So that will be the output, which is also 1. Now over here we see the first change. Select is 1. Here data of 1 has become 0. So therefore the output is 0. Here the select is 0. So data of 0, which is 1, is the output. So therefore this is working, and here we have seen a way how to define something as simple as a 2:1 mux using a data flow assignment. Let us now take a look at how to describe a sequential circuit, let's say a D-latch. So therefore let us make a new project. Let's say it will be a positive D-latch. So I'll create this Verilog file called D-latch and say OK. So a positive D-latch, or any D-latch for that matter, has inputs D and enable, and has an output, has two outputs rather, Q and Q bar. So therefore, let's say module D-latch. Outputs, we'll call them as Q and Q bar, and inputs are D and enable. So let's declare those outputs. Both Q and Q bar are outputs, and the inputs are D and enable. So one of the things that we can do immediately is to establish a relationship between Q and Q bar. I can say Q bar is equal to not of Q. The tilde is essentially a symbol of not. You can use this in behavioral modeling as well inside the always block. Now let us write an always block that shows the events which will trigger the behavior of the D-latch. So obviously the D-latch is defined for two signals in the sensitivity list, either D or enable. So I'll say always @ D, enable. Begin. Now one of the things you may ask is that I have an assign statement followed by an always block. Can this be done? Yes, this can be done, because the assign statement and always block will run parallel. That is the beauty of Verilog. So I'll say here inside the always block, that is, if enable equals 1, then the value of Q will be equal to D. Then I'll say end, and this end is for the ending of the always block, and finally end module. Okay, this is how it is. So essentially these two operations, what is inside the always block and the assign statement, will run in parallel. Let us see if this simulates. So we can see it has failed with 1 error. We have to put that output reg type for Q and Q bar, well, particularly for Q. So let's run it again. Here what you are seeing is that there is a, you cannot put a register to a continuous assignment. So what I'll do, I will define output reg as q, and I will simply define output q bar. Okay, because q bar is given to a continuous assignment data flow, and this is a procedural assignment. Okay, so q, which is inside the always block, will be declared as a reg type, and q bar, which is outside the always, will be declared as a simple output. Let us now see. Now you can see the compile is successful. So let's simulate and see what happens. Latch. So let us put enable to add wave, D to add wave, and Q bar also to add wave. Initially, let us keep enable as 0. And then we will also force D to 0. Let us see what happens. Now what you are seeing over here is that when the enable is 0, the Q and Q bar status are unknown. So here X means unknown. You can see a red line. Okay, so now let's do one thing. Let us make enable as 1. Let's see what happens. Now you can see when the enable has become 1, D is still 0, and the value of Q has become 0 and Q bar is 1. Now they have come out of their unknown states and have taken some known values. With this, now let us make D as 1, keeping the enable also as 1. Now you can see when enable is equal to 1, the D is equal to 1, and that is followed by Q, or rather the value of Q follows D. Now let me make enable as 0. So what should happen? When enable is 0, the value of D is still 1, and the value of Q continues to be the old value of 1. So does it mean that Q is following D? Let's see. Let's make now D as 0. And again simulate. You see that in spite of the fact now that enable and D are both 0, the Q continues to be 1. So the last assigned value of Q is for the time when the enable was still 1. So this shows an example of a simple D-latch and the possible sources of error in the description if you are not handling registers and wires properly. Let us now see how we can use Verilog to describe a T flip-flop. Let's say a positive edge triggered T flip-flop. So let's create the project. Let's create the Verilog file. So let's define the module. So what happens is, for a T flip-flop, there are 2 inputs, T and clock, and 2 outputs, Q and Q bar. So let's do that. So going by our experience with the D-latch or the D flip-flop, the D-latch, we will have to declare Q as a output reg type variable. While Q bar can be a normal output. We will proceed in a very similar manner what we did for the D-latch. The inputs will be Q and clock, T and clock. So we will do the assign statement. So the assign statement to assign that Q bar will be the complement of Q. And then we will start our always block. Now, for a flip-flop, the definition is the changes in the output will happen only during the edge of a clock. In this case, we are concerned with the positive edge. So we cannot simply write clock. We have to specifically mention which edge it is. Otherwise, the computation will happen in both positive as well as negative edges. So therefore, the keyword that we need to use is called as pos edge, which means positive edge. If you want to use negative edge, you can simply mention neg edge. So we'll say always @ pos edge clock begin. Then I'll say if t is equal to 0, then q, the new value of q is equal to the old value of q. Else q is equal to the complement of the old q. And finally, we'll say end module. Let's save it and run it. You can see that the compilation of this code is successful. But we still have a problem. What is happening over here is that we are seeing either q bar equals not of q, or q is equal to q, or q equals not of q. We don't seem to be giving q any specific value. All right. So if we execute the simulation this way, it may so happen that the initial value of q will be some unknown quantity, or it could even be high impedance. So that is a bit of a concern. So therefore, what we will do is we will write a small piece of code that will initialize the value of q to 0. So the keyword is initial. Begin. Now we will say q equals 0, and then we will say end. So initial and always are very similar in operation. They start running together. So this assign statement, initial block, and this always block, they all start running at the same time. But the difference is initial runs only once, and that's it. Now if you notice, I have put a blocking assignment. This is a non-blocking assignment, this is a blocking assignment. Why have I done this? It's to ensure that only after the initial task of initializing the value of q to 0 is complete, the rest of the operations will take place. These are called as non-blocking assignments, which we have already discussed. Okay, so now let us try and simulate. We will compile once again. It seems to be fine. We'll start the simulation. Okay. We'll go to the wave. We will add clock to the wave. We will add t to the wave. Q and q bar also to the wave. So clock, what I will do, I will give it a period of, let's say, 100. And t, I will initially force it to 0. Okay, let's see what happens. So now that t is 0, you can see some positive edges of the clock have passed. The value of q continues to be 0, because q plus has to be equal to old q so long as the value of t is 0. Now before the next positive edge comes, let's force t to 1. Okay, now what you're seeing is that there's this positive edge and t is also changing at the same time. So as per our convention, the flip-flop will not respond at this edge because it will still consider the old value of t. Okay, so for this point, it is still the old state. Now in the next cycle, what is happening is that t is 1. So now the new value of q is the complement of the old value, which is q bar, that is 1. If I continue giving more and more clocks, what we are seeing is that the q is also kind of like a square wave. It is similar to clock, except that the q has a frequency that is 1/2 of the clock frequency. This is what we had discussed as a divide by 2 circuit. So likewise, you can see the value of q bar is also the exact complement of Q. So this is how you can use Verilog to define a T flip-flop.